good day. So, in this video, let's talk about the data link control protocols. Our discussion so far has concerned sending signals over a transmission link. For effective digital data communications, much more is needed to control and manage the exchange. In this chapter, we shift our emphasis to that of sending data over a data communications link. To achieve the necessary control, a layer of logic is added above the physical layer discussed in Chapter 6. This logic is referred to as data link control or a data control protocol. When a data link control protocol is used, the transmission medium between systems is referred to as a data link. A conversation forms of a two-way communication link. There are a measure of symmetry between the two parties. The message passed to and there is a continual stimulus response. Cyclic action remarks call up other remarks, and the behavior of the two individuals becomes concerted, cooperative, and directed towards some goal. This is true communication. On Human Communication by Colin Cherry. Data link control protocols. To see the need for data link control, we list some of the requirements and objectives for the effective communication between two directly connected transmitting receiving stations. First is the frame synchronization. Data are sent in blocks called frames. The beginning and end of each frame must be recognizable. Next one is flow control. The sending station must not send frames at a rate faster than the receiving station can absorb them. Third is error control. Bit errors introduced by transmission system should be corrected. Next is addressing. On a shared link, such as a local area network or LAN, the identity of the two stations involved in a transmission must be specified. Next is controlled and data on same link. It is usually not desirable to have a physically separated communications path for control information. Accordingly, the receiver must be able to distinguish control information from the data being transmitted. And lastly is link management. The initiation, maintenance, and termination of sustained data exchange require a fair amount of coordination and cooperation among stations. Procedure for the management of exchange are required. Flow control. Technique for assuring that transmitting entities that not overwhelm a receiving entity with data. So, a teacher is always a pride because students learn from teachers. When teacher teaches the lesson, the delivery of the lecture is the flow of teaching, and the speed of teaching are very important. If teacher can deliver more content continuously, student will not certainly cannot give whatever that the teacher teaches. For instance, if the teacher delivers at a very high speed, the student cannot grasp all the content delivered by the teacher. And this is obvious, so the teacher has to figure out what he or she must deliver in order to establish a perfect teaching learning experience. So let's start the session. In the absence of flow control, the receiver's buffer may fill up and overflow while it is processing all data. So this is an example of flow control. We have a device A and B. These two devices are going to communicate with each other. Let's suppose if device A is sending some data frames at a very high speed, but device B is not able to handle that much speed. At one fine point of the time, device B will losing all the data frames that was sent by device A. So before sending the data, both devices must mutually agree upon the flow control mechanism. So we can say flow control is a speed matching mechanism where the receiver should inform the sender at what speed the receiver can handle the data frames, and later it becomes the responsibility of the sender to send at the speed that they mutually agree upon. So what flow control does, it coordinates the amount of data that can be sent before receiving an acknowledgement. In other words, flow control is a set of procedures that tells the sender how much data it can transmit before it must wait for an acknowledgement from the receiver in networking. We consider both sender and receiver, but in flow control, we are mainly focusing on the receiver. Why? Because if there is a fast sender and there is a slow receiver, this will always cause a problem because the receiver cannot handle the speed of data reception that was sent by the sender in case if the sender is a slow sender and the receiver is fast receiver, that's not all an issue, so we are always focusing on the receiver. So receiver has a limited speed at which it can process incoming data and a limited amount of memory at which it stores the data and its incoming data whatever sender since the receiver will store anything in its memory and it will be processed. To begin, we examine mechanism for flow control in the absence of errors. The model we will use is depicted in figure 7.1a, which is a vertical time sequence diagram. It has the advantage of showing time dependencies and illustrating the correct send-receive relationship. Each arrow represented a single frame transiting a data link between two stations. The data are sent in a sequence of frames, with each frame containing a portion of data and some control information. The time it takes for a station to emit all of the bits of the frame and to the medium is transmission time. This is a proportional time to the length of frame. The propagational time is the time it takes for a bit to traverse the link between source and destination. For this section, we assume that all frames that are transmitted are successfully received, no frame are lost, and none arrives with errors. Furthermore, frames arrive in the same order in which they are sent. However, each transmitted frame suffer an arbitrary and variable amount of delay before reception. Stop and wait flow control. The simplest form of flow control, known as stop and wait flow control, works as follows. A source entity transmits a frame. After the destination entity receives the frame, it indicates its willingness to accept another frame by sending back an acknowledgement to the frame just received. The source must wait until it receives the acknowledgement before sending the frame. The destination can thus stop the flow of data simply by withholding acknowledgement. This procedure works fine and indeed can hardly be improved upon the message is sent in a few large frames. However, it is often the case that a source will break up a large block of data into smaller blocks and transmit the data in many frames. This is done for the following reasons. First, the buffer size of the receiver may be limited. Second, the longer the transmission, the more likely there will be an error, necessitating retransmission of the entire frame. With smaller frames, errors are detected sooner and a smaller amount of data needs to be retransmitted. Last, on a shared medium, such as LAN, it is usually desirable not to permit one station to occupy the medium for extended period, thus causing long delays at the other sending stations. So we have here in the situations where the bit length of the link is greater than the frame length. Serious inefficient result. This is illustrated in figure 7.2. In this figure, it is shown that the transmission time is normalized to 1 and the propagation delay is expressed as a variable a. Both parts of 7.2 A and B consist of a sequence of snapshots of the transmission process over time. In both cases, the first four snapshots shows the process of transmitting a frame containing data, and the last snapshot shows the return of small acknowledgement frame. Note that for A is greater than 1, the line is always underutilized, and even for A is less than 1, the line is inefficiently utilized. In essence, for very high data rates, for very long distances between sender and receiver, stop and wait flow control provides an efficient line utilization. Sliding windows flow control. The essence of the problem described so far is that only one frame at a time can be in transit. Efficiency can be greatly improved by allowing multiple frames to be in transit at the same time. Consider two stations, A and B, connected via a full duplex link. Station B allocates buffer space for W frames. Thus, B can accept W frames and A is allowed to send W frames without waiting for any acknowledgements. To keep track of which frames have been acknowledged, each is labeled with a k-bit sequence number. This gives a range of sequence numbers of 0 to 2k minus 1, and frames are numbered modulo 2k with a maximum window size of 2k minus 1. The window size need not be the maximum possible size for a given sequence number length k. B acknowledges a frame by sending an acknowledgement that includes the sequence number of the next frame expected. This scheme can also be used to acknowledge multiple frames and is referred to as sliding window flow control. Most data link control protocols also allow a station to cut off the flow of the frames from the other side by sending a receive not ready or the RNR message, which acknowledges frames but forbids transfer of future frames. Each data frame includes a field that holds a sequence number of that frame plus a field that holds a sequence number used for acknowledgement. So, we have here the figure 7.3 is a useful way of depicting the sliding windows process. It assumes that the use of a 3-bit sequence number so that frames are numbered sequentially from 0 through 7, and then the same numbers are used for subsequent frames. The shaded rectangle indicates the frames that may be sent. In this figure, the sender may transmit 5 frames beginning with frame 0. Each time a frame is sent, the shaded window shrinks. Each time an acknowledgement is received, the shaded window grows. Frames between the vertical bar and the shaded window have been sent but not yet acknowledged. As we shall see, the sender must buffer these frames in case they need to be retransmitted. An example is shown in figure 7.4. The example assumes a 3-bit sequence number field and a maximum window size of 7 frames. Initially, A and B have windows indicating that A may transmit 7 frames, beginning with frame 0. After transmitting 3 frames, without acknowledgement, A has shrunk its window to 4 frames and maintained a copy of the 3 transmitted frames. The window indicates A may transmit 4 frames, beginning with frame number 3. B then transmit an RR, or the receive ready, 3, which means I have received all frames up to the frame number 2, and I am ready to receive the frame number 3. In fact, I am prepared to receive 7 frames, beginning with frame number 3. With this acknowledgement, A is back up to permission to transmit 7 frames, still beginning with frame 3. Also, A may discard the buffered frames that has now been acknowledged. Sliding window flow control is potentially much more efficient than stop and wait flow control. The reason is that with sliding window flow control, the transmission link is treated as a pipeline that may be filled with frames in transit. By contrast, with stop and wait flow control, only one frame may be piped at a time. So, this is the example of figure 7.4 of sliding window protocol. Error control techniques. Error control refers to mechanism to detect and correct errors that occur in the transmission frames. The model that we will use, which covers the typical case, is illustrated in figure 7.1. As before, data are sent in a sequence of frames, arrive in the same order in which they are sent, and each transmitted frame suffers an arbitrary and potentially variable amount of delay before reception. In addition, we admit that possible of two types of error. First is lost frame. A frame fails to arrive at the other side. In the case of a network, the network may simply fail to deliver a frame. In the case of direct point-to-point data link, a noise burst may be damage to a frame to the extent that the receiver is not aware that a frame has been transmitted. Next one is the damaged frame. Damaged frame is a recognizable frame that arrived but some of the bits are in error, have been altered during transmission. The most common techniques for error control are based on some or all the following ingredients. First is error detection. The detection detects the destination that are in error using the technique described in the preceding chapter and discards those frames. Second is positive acknowledgement. The destination returns a positive acknowledgement to successfully receive error-free frames. Retransmission after timeout. The source retransmits a frame that has not been acknowledged after a predetermined amount of time. Next is the negative acknowledgement and retransmission. The destination returns a negative acknowledgement to frames in which an error is detected. The source retransmits such frames. Next one is the automatic repeat request or the ARQ. Collectively, these mechanisms are all referred to as automatic repeat requests. The effect of ARQ is to turn the potentially unreliable data link into a reliable one. Three versions of ARQ have been standardized. First is stop and wait ARQ. Second, go back and ARQ. And the last one is the selective reject ARQ. All of these forms are based on the use of the flow control techniques. Stop and wait ARQ. This is one of the three versions of ARQ that has been standardized. It is based on the tap and wait flow control technique outlined previously. The source stations transmit a single frame and then must await an acknowledgement. No other data frames can be sent until the destination station's reply arrives at the source station. Two sorts of error could occur. First, the frame that arrives at destination could be damaged. The receiver detects this by using the error detection technique referred to earlier and simply discards the frame. To account for this possibility, the source station is equipped with a timer. After the frame is transmitted, the source station waits for an acknowledgement. If no acknowledgement is received by the time the timer expires, then the same frame is sent again. Note that this method requires that the transmitter maintain a copy of the transmitted frame until an acknowledgement is received for the frame. Second is the sort of error. This damaged acknowledgement, which is not recognizable by A, which will therefore time out and resend the same frame. So, here in figure 7.1, it gives an example of the use of stop and wait ARQ, showing the transmission of a sequence of a frame from source A to a destination B. The figure shows the two types of errors just described. The third frame transmitted by A is lost or damaged, and therefore B does not return an acknowledgement. A times out and transmit the frame. Later, A transmit a frame labeled A1, but the acknowledgement 0 for the frame is lost. A times out and retransmit the same frame. When B receives two frames in a row with the same label, it discards the second frame but sends back an acknowledgement 0 to each. Go back and RQ. Go back and ARQ. This form of error control based on sliding window flow control is commonly used. The form of error control based on sliding window flow control that is most commonly used is called go back and ARQ. In this method, a station may send a series of frames sequentially numbered modulo some maximum value. The number of an acknowledgement frames outstanding is determined by window size. Using the sliding window flow control technique, while no errors occur, the destination will acknowledge incoming frame as usual, ready receive, or piggyback acknowledgement. If the destination station detects an error in a frame, it may send negative acknowledgement or reject for that frame as explained in the following rules. Thus, the source station, when it receives a rejection, must retransmit the frame in the errors, plus all succeeding frames that were retransmit in the interim. Selective reject ARQ. It is also called selective retransmission. With selective reject ARQ, the only frames retransmitted are those that receive a negative acknowledgement, in this case called SREG, or the selective reject. Selective reject would appear to be more efficient than go back N because it minimizes the amount of retransmission. On the other hand, the receiver must maintain a buffer large enough to save post-selective reject frames until the frame is error is retransmitted and must contain logic for reinserting the frame in the proper sequence. Selective reject is a useful choice for a satellite link because for a long propagation delay involved. So we have an example in figure 7.6, the frame flow for go back and ARQ. Because of the propagation delay on the line, by the time that an acknowledgement, positive or negative, arrives back at the sending station, it has already sent at least one additional frame beyond one being acknowledged. In this example, frame 4 is damaged. As you can see, frames 5 and 6 are received out of order and are discarded by B. When frame 5 arrives, B immediately sends a reject 4. When the reject to the frame 4 is received, not only frame 4 but frame 5 and 6 must be retransmitted. Note that the transmitter must keep a copy of all unacknowledgement frames. It also shows an example of retransmission after timeout. No acknowledgement is received for frame 5 within the timeout period. So A issues and receive ready to determine the status of B. Figure 7.6 illustrates the selective reject ARQ. When frame 5 is received out of order, B sends a selective reject 4, indicating the frame 4 has not been received. However, B continues to accept incoming frames and buffer them until a valid frame 4 is received. At that point, B can place the frames in the proper order for delivery to a higher layer software. High-level data link control, or the HDLC. The most important data link control protocol is the HDLC. Not only is the HDLC widely used, but it is the basis for many other important data link control protocols, which use the same or similar formats and the same mechanisms as employed in HDLC. To satisfy a variety of applications, high-level data link control defines three stations. First, the primary station, responsible for controlling the operation of the link. Frames issued by the primary are called commands. Second, secondary station, operates under the control of the primary station. Frames issued by secondary are called response. Third, combined station, combines the feature of primary and secondary. A combined station may issue both commands and responses. It also defines tooling configurations. Next is the unbalanced configuration. Consists of one primary and one or more secondary stations and support both full duplex and half duplex transmission. Last is the balanced configurations. Consists of two combined combinations and supports both full duplex and half duplex transmission. The HDLC data transfer modes. HDLC defines three data transfer modes. First, the normal response mode or the NRM, used with an unbalanced configuration. NRM is used on multi-drop lines, in which a number of terminals are connected to the host computer. Next one is a asynchronous balance mode or the ABM. Used with a balanced configuration, either combined station may initiate transmission without receiving permission from the other combined station. It is most widely used of the three modes. It makes more efficient use of a full duplex point-to-point link because there is no pooling overhead. And last is the ARM or the asynchronous response mode, used with an unbalanced configuration. The secondary may initiate transmission without explicit permission of the primary. The primary still retains responsibility for the line, including initialization, error recovery, and logical disconnection. ARM is rarely used because it is applicable to some special situation in which a secondary may need to initiate transmission. HALC uses synchronous transmission. All transmissions are in the form of frames, and a single frame format suffices for all types of data and control changes. So we can see in figure 7.7 depicts the structure of the HDLC frame. The flag, address, and control fields that precede the information field are known as a header. The frame, check sequence, and the flag fields following the data field are referred to as a trailer. So flag fields delimit the frame at both ends with a unique pattern. 0, 1, 1, 1, 1, 1, 0. Single flag may be used as the closing flag for one frame and the opening flag for the next. On both sides of the user network interface, receivers are continuously hunting for the flag sequence to synchronize on the start of the frame. While receiving a frame, a station continues to hunt for the sequence to determine the end of frame, because the protocol allows the presence of arbitrary bit patterns. There is no assurance that a pattern 0, 1, 1, 1, 1, 1, 1, 0 will not appear somewhere inside the frame, thus destroying synchronization. To avoid this problem, a procedure known as bit stuffing is used. For all bits between the starting and ending flags, the transmitter inserts an extra 0 bit after each occurrence of five ones in the frame. After detecting a starting flag, the receiver monitors bit stream. When a pattern of 5 ones appears, the 6th bit is examined. If this bit is 0, it is deleted. If the 6th bit is a 1 and the 7th bit is a 0, the combination is accepted as a flag. If the 6th and 7th bits are both 1, the sender is indicating an abort condition. It shows an example of bit stuffing. The figure 7.8, we will note that in the first two cases, the extra 0 is not strictly necessary for avoiding a flag pattern, but is necessary for the operation of the algorithm. Address field. The address field identifies the secondary stations that transmitted or is to receive the frame. This field is not needed for point-to-point links but is always included for the sake of uniformity. It is used to allow the primary to broadcast a frame for reception by all secondaries. HDLC defines three types of frames, each with a different control field format. Information frames, or the iframes, carry the data transmitted over the user. Additionally, flow and error control data using the ARQ mechanism are piggybacked on an information frame. The S-frames, or the supervisory frames, provide the ARQ mechanism when piggybacking is not used. The U-frames, or the unnumbered frames, it is used to provide supplemental link control functions. The first one or two bits of the control field serves to identify the frame type. Figure 7.7, C and D, as you can see, Its use is explained in the discussion of HDLC operation later in this chapter. Control field. All of the control field formats contain the pole final bit. Its use depends on context. Typically, in command frames, it is referred to as P bit and is set to 1 to solicit. A response frame from the peer HDLC and HDLC in response frames, it is referred to as the F bit and is set to 1 to indicate the response frame that transmitted the result of soliciting command. Note that the basic control field for S and I frames uses their bits sequence numbers. With the appropriate set mode commands, an extended control field can be used for S and I frames that employ 7-bit sequence numbers. U frames always contain an 8-bit control fields. Information and Frame Check Sequence, or the FCS. It is present only in I frames and some in U frames. The field contains any sequence of bits, but must consist of an integral numbers of octets. The length of the information field is variable up to the some system defined maximum. The FCS, or the frame check sequences, is an error detecting code calculated from the remaining bits of the frame exclusive of the flags, and the normal code is a 16-bit. The CRC CCITT defined in section 6.3, an optional 32-bit. The frame check sequence using CRC 32 may be employed if the frame length or the line reliability dictates this choice. HDLC operation consists of the exchange of I frames, S frames, and the U frames between two stations. The various commands and responses defined for these frames types are listed in the 7.1. These are the HDLC commands and responses. Next is the HDLC operations. The operations of HDLC involves three phases. First, the one side or another initiates the data link so that frames may be exchanged in an orderly fashion. During this phase, the options that are used to be agreed upon. After initialization, the two sides exchange user data and control information to exercise flow and error control. Finally, one of the two sides signals the termination of the operations. Uh, this command serves three purposes. First one is that it signals the other side that initialization is requested. Second, the three modes, the NRM, AVM, and ARM we discussed earlier is requested, and the third one is it specifies whether 3 or 7-bit sequence number are used. If the other side accepts this request, then the HDLC module on the end transmit an unnumber acknowledge or the UA frame back to the initiating side. If the request is rejected, then disconnected mode frame is sent. S frame are also called and used for flow control and error control. The receive ready frame acknowledges the last iframe received by the indicating the next iframe expected. The receive ready is used when there is no reverse user data traffic or the iframes to carry an acknowledgement. Receive not ready or the RNR acknowledge an iframe as the receive ready but also asks the peer entity to suspend the transmission of iframes. The selective reject is used to request retransmission of just a single frame. Either HDLC module can initiate a disconnect, either on its own initiative if there is some sort of fault or the request of the higher layer user, and HDLC issues a disconnect by sending a disconnect disk frame. The remote entity must accept the disconnect by replying with a UA and informing its layer 3 user that the connection has been terminated. Any outstanding acknowledged iframes may be lost, and the recovery is responsibility of higher layers. So better understand HDLC operations. Several examples are presented in figure 7.9. So first we have the example A, link setup and disconnect. So it shows the frame involved in link setup and disconnect. The HDLC protocol's entity for one side issues an SABM command to the other side and start a timer. The other side, upon receiving the SABM, turns a response and sets local variables and counters to their initial values. So, the same figure in the 7.9a shows the disconnect procedure. One side issues a disk command and the other responds with a UA response. Next is the two-way data exchange. In the figure 7.9b, it illustrates the full duplex exchange of iframes. When an entity sends a number of iframes in a row with no incoming data, then the received sequence number is simply repeated. When an entity receives a number of iframes in a row with no outgoing frames, then the received sequence number in the next outgoing frames must reflect the cumulative activity. But take note that in addition to iframe, data exchange may involve supervisory frames. The third one, that's shown in the figure 7.9, shows an operation involving a busy condition. Such a condition may arise because an HDLC entity is not able to process iframes as fast as they are arriving, or the intended user is not able to accept data as fast as they arrive in iframes. In either case, the entity receives buffer fill up and it has halted the incoming flow of iframes. Using the RNR commands or the receive not ready command in the example, A issues and ready not receive not ready, which requires B to halt transmission of iframes. The station receiving the RNR will usually poll the busy station at some periodic interval by sending and receive ready with a P bit set. An example of error recovery using the reject command is shown in a 7.9d, the reject recovery. In the example, a transmit iframes number 3, 4, 5. Number 4 suffers an error and it is lost. And while when B receives iframe number 5, it discards this frame because it is out of number, out of order, and sends and reject with a number of 4. It causes A to initiate the transmission of iframes previously sent. Beginning with frame 4, A may continue to send additional frames after the transmitted frames. Last is the timeout recovery that's shown in the figure 7.9e. It is an example of error recovery using a timeout is transmit iframe number 3 as the last in a sequence of iframes. The frame suffers an error. B detects the error and discards it. However, B detects that error and discards it. However, B cannot send and reject because there is no way to know if this was an iframe. If an error is detected in a frame, all of the bits of the frame are suspect, and receiver has no way to act upon it. However, A would have started a timer as the frame was transmitted. This was a timer has duration long enough to span the expected response time. When the timer expires, A initiates recovery action. This is usually done by pulling the other side when and receive ready command with the p bit set to determine the status of the other side because the poll demands a response. These examples are not exhaustive. However, this should give a reader a good feel for the behavior of HDLC. So, last, we have the summary of our report, what we discussed. First, the flow control, and its type, the stop and wait flow control, sliding window flow control. Next one is the error control. It has stop and wait ARQ, go back and ARQ, selective reject ARQ. And lastly, it's all about high level data link control or the HDLC and its basic characteristics, frame structure, and operation. So that's all for today. I hope you have learned something in my video and of what we discussed. So thank you. Have a good day.